Now let's look at the third example. So here I'm going to consider a function f of x equal to 1 over x squared on the interval I, where I is going to be from 0 to 1, not including 1. Again, I want to verify that this function is continuous on I by using epsilon delta definition of continuity. All right, so let's see what we can do here. I'm going to choose again any x0 between 0 and 1, and also select an arbitrary epsilon greater than 0. And once again, we want to show that, that there exists delta greater than 0 such that x minus x0 less than delta, that this would imply that f of x minus f of x0 is less than epsilon. Okay, so let's see what we can say. So suppose, or consider, f of x minus f of x0 Now, what is that? That would be 1 over x squared minus 1 over x0 square absolute value. And we can simplify this to look like absolute value of x, right? If I put these on the common denominator, absolute value of x squared minus x0 squared over absolute value of x squared times x0 squared, but both are positive, so it's just x0 squared times x squared. All right, so we have that. Then again, we can decompose x squared minus x0 squared into a product x minus x0 times x plus x0 divided by x0 squared, x0 squared times x squared. And I can bound this from above, right? Again, because x and x0 lie between 0 and 1. That means that x plus x0 on the top is going to be less than 2, right? If both x and 0 are equal to 1. So this should be less, strictly less, because they cannot actually be equal to 1. 2 over x0 squared times x squared, x minus x0. I can try to make this quantity less than epsilon, but then if I want to obtain a bound on x minus x0, I'll have to multiply both sides by 2x0 squared times x squared, which will make the potential delta dependent on x, and it cannot be dependent on x. So I have to come up with some sort of approximation or some sort of a bound that will allow me to deal with this. So let's see what we can have here. So let me just write this, as I said, that this is less than, let's try this first, less than epsilon. So saying that would be the same thing as saying I want x minus x0 to be less than x0 square x squared times epsilon. And of course, x0 here, right, is a fixed number. And x is some number between 0 and 1. And in principle, x can be as close to 0 as you wish. If x is close to 0, then this expression on the right-hand side is going to be close to 0 itself. So x minus x0 squared, x minus x0 in this case, is going to be arbitrarily small, arbitrarily close to 0, which would seem to indicate that if I consider x on the entire interval from 0 to infinity, then x minus x0 is not going to be bounded by any number, right? It can be arbitrarily small. Okay, so what can I do here? I can try to, just like we did before, I can try to make the following approximation, or make the following estimate. So if x minus x0, so this is not going to give me anything. So I'm just going to get rid of this statement. And in fact, still too early to make this less than epsilon. What I want to do is a usual thing. I want to find some constant bound on this quantity from above so that I can then make constant times x minus x0 to be less than epsilon, and that will allow me to find delta. All right, so here 2 over x0 squared is kosher, right? Because x0 is some fixed number between 0 and 1. So this is a constant. I don't need to worry about this. But I have to worry about x squared in the denominator. Right, because if x is small enough, then I can make this fraction arbitrarily big, which is not going to be good in trying to make the whole product to be less than epsilon. So before we continue, let's make the following assumption. So before continuing, now, here the only thing that I actually want to make happen is that I want x to stay away from 0. And how do I make x stay away from 0? I have to take it sufficiently close to x0. So x0, again, is a fixed number. Maybe it is very small, but it's fixed. Then how close do I want to take my x to x0? Again, for continuity, it is enough to verify epsilon delta definition for x's that are arbitrarily close to x0. So I'm going to assume that x minus x0, the distance between x and x0, I want to stay away from 0, so I want the distance to be, for example, less or equal than what? Than x0 over 2. And x0 is a positive number, so I don't need to take any absolute values here. Right, so if x minus x0 is less or equal than x0 over 2, then that will imply that x should stay away from the origin. How do I see that? This is the same thing as saying minus x0 over 2 is less or equal than x minus x0 less or equal than x0 over 2. And then if you add x0 to all three sides, you have that x0 over 2 is less or equal than x less or equal than 3x0 over 2. And I only care about the lower bound here. So as long as I'm assuming that x minus x0, that the distance is less than x0 over 2, then clearly x has to stay half a distance from x0 to the origin, away from 0. All right, and so if that is true, if I go back to my computation, so let's call this computation star, then I have that 2, so going back to star, I have that 2 over x0 squared times x squared times x minus x0. What have I got about x? So x is, under my assumption that x minus x0 is less or equal than x0 over 2, x is greater than x0 over 2. So 1 over x must be less than 1 over x0 over 2. So this should be less than or equal to 2 over x0 squared. And if I replace the denominator with a smaller number, the whole thing becomes bigger. So x0 over 2 quantity squared, and this is still x minus x0. All right, so this I can simplify. 2 is in the second denominator, 2 squared is in the second denominator, so it goes up to the numerator, becomes 8. In the denominator I have x0 squared times x minus x0, and I want now to make this less than epsilon. So this implies that x minus x0 should be less than x0 squared epsilon divided by 8. Right, again, x0 is a fixed number, right, because I'm testing for continuity at x0, so therefore I can make this my delta. And because this implication goes both ways, if I choose x minus x0 less than delta, then this inequality holds, then this holds, then this guy is less than epsilon, so this guy, which is the same as that guy, he is less than epsilon, and therefore f of x minus f of x0 should be less than epsilon. So the definition of continuity is verified at an arbitrary x0 between 0 and 1. Continuity of a function f of x equal to 1 over x squared. What I want to do now, I want to again address a question of how does delta behave here? Is there a delta that is going to work for all x0s, right? Same delta that will work for the definition of continuity for all x0s between 0 and 1 at once. So once again, as before, let me actually, because I used stars to denote items, so let's call this 1. So this formula is, this set of inequalities is referred to as being 1. So the next question is there a delta greater than 0 that works in the definition of continuity for all x0 between 0 and 1. So as we discussed before, this delta must be then, remember this is delta that depends on x0. This common delta must be, we put, so this common delta should be a minimum or an infimum of delta of x0 when x0 belongs to the interval between 0 and 1, right? So if I want to choose the common delta that works for all x0, I'll take all deltas corresponding to different x0s, and I have to select the smallest, because then if x minus x0 is less than the smallest possible delta of x0, it's less than all deltas of x0. And so then I satisfy a definition of continuity at all points at the same time. Okay, so what is it here? It is the minimum of x0 squared epsilon over 8 among all x0 between 0 and 1, and it's clear here that this minimum is equal to 0. And so then the conclusion is that there is no common delta greater than 0 for all x0 that belong to the interval from 0 to 1. Again, if we try to illustrate this pictorially, let me do this here. So I need to draw a graph of f of x equal to 1 over x squared. The graph is a hyperbola like this. And so again, I have 2 points, x0 and x. X can be lower and higher than x0. So then they will lie in the following window. F of x0 and f of x in this case is lower. And let's say that I want the window to have the size epsilon. And I want to find the common delta that works in the interval from 0 to 1. What does it mean? It means that if the 2 points on the y-axis are going to differ by the amount small than epsilon, I have to make sure that 2 points on x-axis have to be smaller than some delta. But such smaller delta certainly is not going to exist, because if you take this window and you slide it along y-axis towards infinity, then the projection onto x-axis, these 2 points, are going to get closer and closer to the origin and closer to each other. So as you slide the way to infinity along the y-axis, the difference between x0 and x becomes smaller than any prescribed number, while the distance between y values is still equal to epsilon. So this graph, again, remember that we made a connection with steepness of the graph. In this case, the graph becomes steeper as x0 gets closer and closer to 0, and it becomes, in fact, arbitrarily steep, right? So that means that the slope of the graph in this case is unbounded, similar to what we saw with the example of x squared, right, on the interval from 0 to infinity. The slope of this graph also is unbounded, right? Because the slope is 2x, if x is between 0 and infinity, the slope is unbounded. And so there is no common delta in this case, if there were, it would have been equal to 0, but 0 is not a legitimate delta. And it's the same deal here. It seems that the common delta must be equal to 0, and again, 0 is not a delta that is allowed in the definition of continuity. All right. Actually, let's do 2 more examples, and then we'll talk about the theory that applies to these examples. Let me compress things a little bit before I move on to that next example. So I'm going to consider another function. Oops. And now what we know what we're going to look for. So if we want to see if we have a common delta that works for all x0 that belong to the domain of your function, we will have to somehow, at least one ingredient that we want to examine, it would be the steepness of the graph of the function that you're dealing with. So as an example 4, I'm going to look at the function sine, so f of x is equal to sine of 1 over x, and x I'm going to take between 0 and pi over 2. Right, that is the graph that we actually studied before when we talked about continuity at the origin, but right now I'm considering this functional interval from 0 to pi over 2, and I want to know if this function is going to be continuous everywhere there, and if there is, in the epsilon delta definition, if there is going to be a delta that is common to all points on the graph of this function. So let's see. So in this case, actually, I'm going to try to answer this question pictorially, not by writing some analytical calculations, but pictorially with understanding that if you want to, you should be able to write a corresponding proof. So what I want to do is I want to sketch the graph of this function. And what I see is if x goes to infinity, so try to sketch the graph. The graph. So we can use the standard graphing procedure for an equation. So in this case, things that I will see is that if x goes to infinity, then 1 over x goes to 0. And if 1 over x goes to 0, then sine of 1 over x, that goes to 0 as well. Right, so that is correct. And so that means that this function f has a horizontal in fact, let me, okay, so I'm doing what I'm doing here. F has a horizontal asymptote when x goes to plus infinity, which of course is irrelevant to me here because x is between 0 and pi over 2. But I just want to sketch a graph And the fact that I have a horizontal asymptote is going to be relevant in the next example. So if I attempt to, roughly speaking, sketch the graph of this, then what I know is that if x goes to infinity, then my function is going to go to 0. So it will have a horizontal asymptote y equal to 0 at plus infinity. Not only that, but if x goes to plus infinity, 1 over x is a small positive number, and sine of a small positive number is positive. So that means that I'm approaching this horizontal asymptote from above. Okay, so now what happens if x goes to 0 plus? So on the other hand, if x goes to 0 from the right hand side, then 1 over x will go to plus infinity, and sine of 1 over x is going to oscillate between maximum and minimum values of sine, which are minus 1 and 1. So this guy oscillates between minus 1 and 1. And it will have infinitely many oscillations, right? So therefore, what we will get is this. As x goes closer and closer to 0, then my function that was fairly nice before, this graph is not very good, but the function will start oscillating between minus 1 and 1 like crazy. And the closer to 0 you go in x, the finer and finer oscillations between minus 1 to 1 and 1 you will see. All right. So my question is, I don't want to do epsilon delta definition here, but if I did, would we be able to find delta common to all x in the epsilon delta definition of continuity? So let me write this question. So thinking about the definition of continuity at x0, is there a common delta?
Parents or one other.
Is there a common delta that works for all x0 between 0 and pi over 2? And I claim, based on the picture, that such x0 is not going to exist. Because once again, if I take an epsilon size interval on y-axis, and then I look at the difference between x and x0, how small the difference between x minus x0 has to be to make the difference between f of x and f of x0 less than epsilon, I can see here that, so for instance, if those are my x and x0, then the distance is some fixed number delta. But as I move along up and down branches of this function closer and closer to 0, then I would see that the steepness of a graph is going to grow without bound again. And therefore, the difference between the values of x and x0 that will guarantee that f of x minus f of x0 lies within this interval, the difference between x and x0 will go to 0 as the graph becomes steeper and steeper closer to x equal to 0. So then the common delta, if it would exist, it would again have value of 0. So that means that the answer here is going to be no. So no such delta, because the graph is becoming infinitely steep as x converges to 0. In that sense, the graph that we're seeing here, even though the function here does not go to infinity as x approaches 0, it still behaves in a way similar to the previous example where at 0 the graph was going in a decreasing way, or increasing if I go from right to left. As you approach 0, the graph goes to plus infinity. So it becomes infinitely steep because y becomes infinitely large. In this case, y does not become infinitely large. Y is always between minus 1 and 1, but because the function is oscillating faster and faster, then cumulative effect is exactly the same as in the previous example. So the graph becomes infinitely steep. Again, I can verify that, for instance, by using the derivative, right, by finding a derivative of this function. And regardless how I do it, from a picture or by taking a derivative, I can see that the slope becomes arbitrarily large as x gets closer to 0. So no common delta. I'm not going to write this down, but we can just take a look here. So let's say pi over 2, this is not really true, but let's suppose that pi over 2 is down here somewhere. So far I looked at the interval from 0 to pi over 2. Now what about the interval from pi over 2 to infinity? Is there a common delta in this case? And I claim that in this case there is a common delta y because, again, just like before, if I look at my graph from pi over 2 to infinity, I can see that the slope of the graph is bounded again on this entire interval from pi over 2 to infinity because since I have a horizontal asymptote at infinity, the graph at infinity is infinitely shallow, right? It's essentially more and more parallel to the x-axis. So the largest slope will occur somewhere, I don't know if it is, maybe at pi over 2 or at some point close to pi over 2. And therefore, if the slope is bounded, we said before, then that means that the difference between values of f at different points, both of which are larger than pi over 2, will be bounded from above by some number times x minus x0. And so in that case, then there is a common delta, right? Because the slope of the graph is bounded on the interval from pi over 2 to infinity. All right, and actually the final example I'm going to do next time. So just to summarize what we have seen here, we have seen functions on bounded intervals like minus 1 to 1, x squared on a bounded interval from minus 1 to 1. For that function, in the absolute delta definition, I was able to select a delta which was common to all points between between 0 and between minus 1 and 1. Then after that, when we consider x squared on an infinite interval, interval of the infinite length, between -1 and 1, the derivative of x squared is bounded by 2. So the rise or run for this function is always less or equal than 2. That allows us to find delta, which was common to everybody. But for f of x, where you look at x squared in the interval from 1 to infinity, or from 0 to infinity, in that case, there is no common delta because the graph becomes infinitely steep as you go away to infinity. And it was the same for 1 over x squared and sine of 1 over x, as long as you have an interval which is arbitrarily close to an open interval with the left-hand point being equal to 0. In both of these cases, my function became arbitrarily steep as x gets close to 0, and so that causes delta to become smaller and smaller, and there is no bound on how small it can become, so delta is going to be equal to 0, so delta is not going to work in the third and the fourth case. But there will be a common delta on the interval from pi over 2 to infinity, because there the slope is bounded, right, for this function. And so the function is uniformly continuous on any interval that does not contain 0, and it is not, okay, I already used the word uniformly continuous, and it is uniformly continuous when x is greater than or equal to pi over 2. Uniformly continuous simply means what I've been talking about here for hours now. It just means that there is a common delta in a definition of continuity that works for all x's at once, which, as we discussed, in a sense, means that the graph has some bound on how steep it can be. But in the example that I'm going to do next time, we'll see that it's still possible for the slope to become infinity, be unbounded, but it can happen only at finitely many points. And you still will be able to find sometimes a common delta. But that will be discovered next time.